In this lesson, we will look at finding the volume of a solid of revolution. This is different than the previous lesson where we looked at the volume of a known cross-sectional figure in that we are going to be revolving a graph around one of the axes. When we do that, we always get a consistent shape. It will be, in this first example here, it talks about a disk. So in the previous examples, we had square cross-sections or semicircles or any really shape that we wanted. Today, they will all be the same shape. They will all be disks. When we do that, we need to use, again, the area formula for that specific shape. So a disk is actually a circle. If we look right here in the first formula given to us on this page, it says a equals pi r squared. That, of course, is the area of a circle. So that's what we're going to be integrating today. It's going to be the same formula for all of these as long as they're a disk. There are going to be some other more intricate versions of this that we'll see as well. So what we really just need to do is figure out what our function is, figure out the limits of integration, and then plug this thing in. You'll see I've got the calculator up. It's all going to be calculator work once we get to that point. So for this first example here, they've done a really good job with the pictures. Obviously, very hard to draw these things three-dimensional on a two-dimensional plane. So they've got a really nice example here with the picture. The top one there, the blue graph, is y equals the square root of x. And they ask us, you can see that indicated by this little arrow here, to rotate it around the x-axis. So when we do that, we will end up with this shape that we have here on the bottom. It's not quite a cone, so we couldn't use the volume of a cone formula. It's a different shape. We don't have a geometric formula for it, so this is the only way that we can find the volume. In the previous lesson, we had, a pyramid. We can find that using geometric formulas, cones, cylinders, things like that. Today, we're not going to have any shapes that we know a formula for. So here's what we would do. We start by finding our limits of integration. So the limits of integration are going to be whatever the numbers for the axis, the letter you're using. So we're going to be integrating with respect to x, so that's where we're going to get our limits of integration from the x-axis. If you notice, those are the only two numbers that are on this entire graph, are the two numbers on the x-axis. So we would set up our integral as the integral from 0 to 4 of pi r squared. The radius is going to be the function, so it's going to be pi square root of x squared dx. There's a lot we can do with this to clean it up. We could even probably do this by hand if we really wanted to, since it's the square root of x squared. It's an easy integral, but it's good practice to get used to using the calculator because there are going to be a lot of problems that we have no chance of doing by hand. A few things, you don't have to put it in the calculator like this if that's a bit clunky. I'll show you what I mean here. So if we go onto the calculator and we start out with exactly what's there. So the integral from 0 to 4 of pi square root of x squared, we'll get 8 pi. And that's the answer. That's the volume of this figure. It is 8 pi. If we think about a cone of the same size, I don't know how we'd think about a cone of the same size. It doesn't work that way. Don't think about that. Let's just go back to this formula. So we can rearrange and kind of simplify this formula. What we can do is we can bring pi out to the front. So it doesn't really make a difference in this problem, but when we get into some more involved problems later on, it's going to be a good idea to bring pi out front. That way we don't have to worry about extra set of parentheses on the inside of the equation. You could, like I said, to start, simplify the integrand to be just x. You should get the same answer this way of 8 pi. This second iteration that I've drawn in, you don't need to do that. There's no reason to do that simplifying unless you're concerned about where everything is with parentheses. And if you are proficient with putting things in the Inspire, then the extra sets of parentheses shouldn't be a problem. You should get the same answer, the 8 pi that we got. So this is kind of a crazy example here. They're talking about creating a sphere by rotating a circle. So we're not going to actually do this example, but it's a fun example that I like to just see every time to go through this because we do know the area, the volume formula rather, for a sphere, and it is directly related to the area of a circle. So pi r squared, 4/3 pi r cubed. It's not a perfect antiderivative, but it's pretty dang close. So that's in there. They go through all of this. There's a lot more than I necessarily want to do on that one, but just for a little bit of reference there. Okay, let's see if there is one more example in here. Not yet. Okay, so I'm going to draw another example in here before we get to that next slide. So this you can pause the video and take a look at and try to do yourself if you'd like. Our function is 2 plus x cosine x. We are rotating it over the x-axis. And our limits are from -2 to 2. So if you'd like to take a moment, put that in the calculator, pause the video now, and go ahead and do that. Okay, so hopefully you've come up with an answer here. With this one, we would not want to try to do this by hand. X cosine x, that's not going to be a fun integral to solve by hand. So we're just going to go straight to the calculator on this. To set it up, we are using disks. I don't even have a great picture of what this is. I'll draw one really quickly by hand here. So if we take our xy axis and we do 2 plus x cosine x, it's going to look something like this, from -2 to 2. And then when we rotate that, we'll get a solid that looks similar. It's almost like a fish, maybe a vase. Like I said, it's not really easy to draw these by hand. But there we go. There would be our solid. And we have these different cross sections that are all circles of different sizes. Okay, so terrible drawing aside, we hopefully just threw this in the calculator, got an answer here. The integral setup would be the integral, our limits are 2 to 2, -2 to 2, of pi, so you can put that inside, outside, doesn't matter, times the radius, which is just the function, 2 plus x cosine x, quantity squared dx. And then when we go over to the calculator, we're going to get pi parenthesis 2 plus, if you've ever done this, or maybe you did it right now, and you type just x cosine x, your calculator will change it from the standard font to italicized font on these Inspires. If you notice that if that happens, that is not a good thing. What that means is your calculator doesn't like what you've written. It's no longer a function, it is now just letters. So if you ever see that, what needs to happen here is there actually needs to be explicit multiplication between x and cosine, not implicit. If you write x cosine x, it's not going to like that. So make sure you put a little multiplication there. You can open another parenthesis for the cosine, but then you'd have like triple parentheses in there, which can get a little confusing. So whatever you need to do there, but make sure that they both stay in the normal font, and if it goes to italicized, try to notice that and fix it. So we have this, we hit enter, we get this crazy thing. I have no idea what that is, so let's get an approximation. So approximately 52.43. And then whatever units it might be cubed. They didn't give us a unit for this example, but inches, centimeters, miles, whatever it might be. Okay, so those are kind of the basic. We are just rotating it around one of the axes, either X or Y. What we can then do is we can move our solid, or we can have a different axis of rotation. So this is the same function from the first example, the square root of x, and the problem now is to rotate it over the line y equals 1. So we've not changed the function, we've changed the axis of rotation. So there's two ways that you can do it. You can either change where the function sits, or you can change the axis of rotation. Either way, that's going to affect your outcome. If we look at the picture, it's a much smaller blue region, it's a much smaller green solid, so we should get an answer that is less than 8 pi. So how do we account for this change in the graph? Well, it's a really, really easy a way to account for it, and they've shown it to us right here. What's happening is moving this axis of rotation up to 1, we are losing 1 unit from everything when it rotates. So this graph is now 1 unit shorter everywhere. It also changed the limits of integration because this part on the far left here is no longer a space. There's no area underneath that part of the curve since we've cut it at y equals 1. So it does change our limits of integration. Be very aware of that. And it changes what our radius is going to be. So our radius now is the function minus the axis of rotation. And that's always true. The radius is the function minus the axis of rotation. So when we're rotating it on one of the axes, x or y, those values are y equals 0 or x equals 0. So we don't have to really do this because it's just trivial. It's function minus 0. But anytime we have a different axis of rotation, all we do is take the function, subtract the axis of rotation. The axis could be negative, so if they told us that the axis of rotation was -1, it would be square root of x minus -1. So we'd actually end up with much more area there to rotate. So all we do is we take the function, subtract whatever the axis is. When we go to set this up, we do need to make sure that we have everything in the right place for the formula to work. It's still going to be pi r squared. So the radius is going to be your function minus your axis, all of that together squared. So make sure that that subtraction ends up inside the parenthesis with the function. So if you want to take a moment, pause the video, try to set this one up with the integral and go ahead and calculate that out. Okay, so we have the integral. Again, we take our limits of integration from the axis. The x letter is what we're integrating, so we're going to take our limits from the x, so 1 to 4. Pi, inside outside doesn't matter. And then our radius is now the function x root minus the axis of rotation 1, whole thing squared dx. Again, this is something that we want to let our calculator handle. Could we try to do this one by hand? Sure, but why? Why would we? We have the calculator, we should use it. And we do the square root of x minus 1 quantity squared. And it should be less than 8 pi. So we get 7 pi over 6, which is definitely less than 8 pi. And there we go. Okay, so we can rotate a function over the x-axis, no big deal, pi r squared. We can change the axis of rotation. We just do the function minus that axis. That's our new radius that we're squaring. What happens if we change the orientation of what we're rotating? So we can rotate around the y-axis, and to do that using this same method, we need to change the way we have our functions written. So we've had functions f of x, now we're going to go with functions of y. So it says right here, area is a function of y dy, and the radius is a function of y dy. So that's what we're going to do. We can start out with the same functions that we had. So if we go to this one, we would rearrange the functions. So the function y equals square root of x, we'd rearrange that to be x equals y squared, something like that. If they give us the function as something like this, where x is a function of y, then that is a really easy setup, just like we had. When they give us the function in the letter that we're going to rotate the axis on, that's when we use this discs method, this pi r squared method. So when your letter of rotation matches your letter of integration, you're going to use discs, you're going to use pi r squared. So nothing is going to change here in terms of the setup. It's still going to be the integral of pi r squared. The radius is still the function. The only difference now is all of our information is going to be in terms of y. So the limits of integration should come from the y-axis, since we're using y. The function that we plug in for radius should be a function of y, and then it should be dy that you write at the end of the integral. for this, which is actually looks like a bell, for this little bell graph here, go ahead and pause video, write out your integral, and find the volume. Okay, so we have the integral, and we're going to take our limits of integration from the axis that we are working with. So we're working with everything in y this time. So our our limits come from the y-axis. So 1 and 4. All right, so then our function is pi. Radius now is 2 over y, quantity squared dy. And that's what we should be plugging into our calculator. So we take the integral from 1 to 4 of pi 2 over y, quantity squared dy. And we end up with 3 pi. Okay, nothing really different about this problem. They changed the entire orientation of it. We are doing everything in terms of y, rotating on the y, getting our limits from the y, the function is in y. But it's the exact same setup, the exact same work that we just did. If they asked us to rotate it on a different line, so if they asked us to do like the rotation over the line x equals 1, they would give it to us as an x equals line now, a vertical line. We do the same thing. We would do the radius 2 over y minus the axis of rotation minus 1, and we would do the same exact thing that we did in the previous problem. All right, now it's time to, there's another example for that. You can pause that and take a shot at that. This does have the axis of rotation that is shifted. The axis of rotation now is x equals 3. Actually, I'm going to talk about this one for a moment here. So the function they give us is x equals y squared plus 1. Great. The axis of rotation is 3. If we look at this function, the curve, the blue curve, is on the left side of the line x equals 3. So when something like this happens, we're going to have to go back to the volume of, the area between two curves, and remember those concepts to get this correct. So what we need to do for this is the right minus the left. So that's how we found area between two curves. It was either for x's top minus bottom or for y's right minus left. So in this drawing, which of the two parts is farther to the right? Well, that is the line, the axis of rotation, x equals 3. So that is why it's there. Then we're subtracting the right part, so y squared minus 1. So let's just take a look and see what that would potentially do to our integrals. So we have the limits of integration again come from the y-axis, so negative and positive root 2. So we'll do the square root of 2 and we'll do it as they've got it here. So we'll do pi, and we'll type in just 3 minus y squared minus 1. Sorry, plus 1. And then close that, square that whole thing, dy. Got a syntax error. Oh, because I didn't put the 1 in. Okay, so we end up with 64 pi root 2 over 15. Don't care what that is for right now, I'm just going to compare answers. So if we do this the other way, and if we did pi times the function y squared plus 1 minus 3, so if we had them in the wrong order, quantity squared dy, we end up with the same answer. Okay. So it's actually okay if you mess the order up. The proper way to do it is the 2 minus y squared, but if we distributed it the other way, it'd be y minus 2 squared. You're squaring things out, so you're still getting the positives for that, and it's not as huge of a deal. It might be a deal breaker in some problems, so it's best to get the setup correctly, but for this problem, it's actually the same answer either way we set the problem up. Okay, moving on. So we have one more setup to look at today, and that is when we have a second function that we're going to rotate at the same time. So for this problem here, we've got capital R and lowercase r. They're two separate functions of x being rotated together at the same time over the x-axis. So this again goes back to the area information from the previous chapter, where we need to account for which functions outside or inside, top or bottom, left or right, however you want to think about it. I usually think about it as outer and inner. That way it doesn't matter if it's x's or y's. You don't have to worry top, bottom, left, right. It's just outside, inside. So what do I mean by outside inside function? Well, when we take this set of functions and we rotate it, we'll end up with this green shape here. So the outside function is this top curve. It makes the outside of the figure. So you can think about this as, I don't know, maybe like a bowl, something that has an opening in the middle. The outside is the capital R of x, and the inside of the function, the solid, is that lowercase r of x. And as you look, we get these open shapes on the inside, and those are called washers. So washers are a circle with the center punched out, exactly like a washer from like construction building, same idea. The way that we do this is the same as the disks. It's pi r squared, but we have to account for the fact that there are two different radii. So the slides that we have here do use the terms outer and inner, which is good. The outer radius is the capital R of x, the inner is the lower r of x. And what we're doing is we're taking essentially the volume of the outside function, so a big solid object. And then we're going to take the volume of the inside function and subtract that out of the big function. So the way that that looks is pi capital R squared minus pi lower r squared, and we can factor pi out of that to get pi big R squared minus little r squared. And that's how we're going to do this setup. So this would be the time where I would pull the pi outside of the integral. That way it is just a to b of big R squared minus little r squared. This way there's less sets of parentheses, hopefully less confusion, but the most important thing is we have to square the functions independently and then subtract them after. You cannot do r minus r quantity squared. That will never work because we have to take a volume, subtract out a smaller volume. That's how we get this exact shape that they're asking for. So it's big R squared minus little r squared. Each of them gets squared independently. So for this first example of this, they give us the functions y equals negative x plus 3, and then the little r is x squared plus 1. So they've given us two functions. If they give you two functions without a picture, what you want to do right away is graph them. You absolutely have to know which function is outside and which function is the inside. So always graph if you don't get a picture. So there's the first function. Then our second function is x squared plus 1. So we have these two graphs here. They do have natural intersections right here and right here. It's kind of easy to see that that one is 1 and this one is negative 2. So those are kind of the natural limits of integration. The problems will generally say for function 1, function 2, the area between the two curves is rotated over the axis. So they'll always kind of specify where they want it to be, maybe explicitly with the limits for you, or they'll say the area enclosed by the two figures, and then you need to find the intersection points of them. Sometimes they're not as obvious as this, and if they're not as obvious, just use the solver back on the first screen. Where am I? There we are. So we just solve the negative x plus 3 equals x squared plus 1. Solving that for x, and it tells us those two solutions. So just in case they're not actual nice numbers to see on the graph, use the solver, find them either way. Okay, So we have our functions, we have our limits of integration, we are ready to write this thing out. The integral from -2 to 1. I'm going to put pi out front to start. I always do, especially for these problems. I've not been doing it for the previous because it doesn't necessarily matter, but here I like to have it out front. The outer function, so that is the -x plus 3 quantity squared minus the inner function, which is x squared plus 1 quantity squared dx. Let's see what we get. So we have -x plus 3 quantity squared minus x squared plus 1 squared dx. And it's 117 pi over 5. So the calculator does a nice job filling in parentheses for us if we don't open them up necessarily at the start. So it's got everything where it needs to be with pi out front. Really wouldn't make a difference if it was on the inside there, but we have an answer 117 pi over 5. Same rules apply if you switch the order of integration, or sorry, the variable of integration to y, you're going to have the same thing. So you're going to need your functions as big R of y and little r of y. It's still outside inside, so the best thing to do would be to graph these. If you're not familiar with how to graph them by hand, just take your calculator, go into menu, go into option 3, graph edit entry, and then go to option 2, which is relation mode. Then you can type in whatever the heck you want. So we have x equals y over 2. We have that, that's the line, that's the inner function, and then x equals square root of y. Okay, so there is our secondary function. And then they intersect there, and they intersect at 0, 0, so that point is at 2, 4. So those are our limits of integration. If you want to take a shot at this one, go ahead and pause the video, set up your integral, and see what you find for the volume. So our limits of integration go from 0 to 4. So we are using the y values, excuse me. So 0 to 4 on the y, since we're integrating with respect to y. Pi, I'm going to put out front. The outer radius, which is the curve, is the square root of y. So I have square root of y, quantity squared, minus the inner is y over 2, the line, quantity squared, and that is dy. Okay, so pi's out front. We have 4 on top, not 44. 0, and then we're going to do exactly as it's written. I know we could probably clean this up and be a lot quicker, but we're just going to write it as is. So y quantity squared minus, and opens that extra parenthesis for us, which is nice. We have then y divided by 2 quantity squared dy. And we get 8/3 pi. Okay, so that is it basically for the washer or disk method. They're the exact same thing. They are pi r squared. The only difference between really all of these is what way you're looking at it. Are you doing x, are you doing y? And is there a second function? But it's always going to be pi r squared. And we're always going to be integrating whatever variable the limits are always going to come from whatever variable we're integrating. So if we're doing it, rotating it over the x-axis, it should be a function of x, and we're going to get our limits from the x-axis. Doesn't matter if it's a washer or a disk, that's how you do it, x, x, x. If you are doing y's, you're going to be a function of y, rotating on the y-axis, using your limits of integration from the same y-axis, y, y, y. So all of that should be the same. Then the two formulas, if it's just one function, it's just pi r squared. If it's two functions, it's always outer minus inner. So there is one more method for integrating solids that we will look at in the next video, but until then.